All right, so the first part of this lab that we are going to do is basically just to kind of give you a more like normally it would be a hands-on sense, but at least you'll get at least a better sense of how your respiratory system kind of changes the air that you breathe in. Um, you know, so the first part of this is basically, let's say this is you breathing in. Whoop, that's bad. So you're taking air that's just, there's air in the room, and it's going down into your lungs, and then you're breathing it out. We're going to look at three different qualities. We're going to think about the temperature of the air. We're going to think about the moisture content of the air. We're going to think about the amount of CO2. What is your prediction? How do you think the inhaled air is going to compare to the exhaled air in terms of temperature?
Exhaled will be warmer.
Right, yeah, so you think about it, you're bringing it down deep into the bowels of your body, into your lungs here. So you're going to be warming it up before it comes out. What about the moisture content?
I'm kind of guessing and just saying higher.
Yeah, remember the whole thing we're looking down the alveoli, everything is all wet and humid down in there. So that's another thing, the moisture content. You're going to be really humidifying things before it comes out. What about CO2?
Higher concentration.
Yeah, I mean, obviously the whole point of the respiratory system is to exhale CO2. If you remember when I was saying like air is, around 80% nitrogen and 20% oxygen, that didn't even leave space for carbon dioxide, right? Carbon dioxide is normally a fraction of a percent of the total air. However, because your lungs are this kind of blind sac down in here, and they're making CO2, and whenever you breathe out, again, you're not breathing out all of the air in there. There's always going to be that dead air, that stale air that stays in there and gets mixed in with the new air you're breathing down, which means that the levels of carbon dioxide down in your lungs are always going to be quite a bit higher than they are outside. Whenever you exhale, you're going to be exhaling much higher levels of CO2 than you would find natively in the air. So in this lab, we have some pretty low-tech ways of measuring some of this stuff, right? Temperature, you're basically gonna like wave it around in the room and look at the temperature, and then you're gonna hold it between your lips and blow on it and look at the temperature. And you'll be able to compare the temperature. What was the air temperature in the room? What's the air temperature that you are exhaling? Water content's even more low-tech. You're basically exhaling on a piece of glass. And basically, especially when hot air cools, and again, we talked about the air coming out of your here is cool. Hotter air can actually hold more moisture. Cooler air can't hold as much moisture. So if you have warm air that has a lot of moisture and you cool it down, like by hitting it on a piece of cold glass, the moisture will crash out. So we are gonna, it's not gonna be a surprise. If again, this is something I kind of it's hard for me to imagine any of you got to this age without ever blowing on a piece of glass and noticing what happened. But we're going to do it now in a more intentional way and think about what are actually the implications of that. For carbon dioxide, we have a bit of a more fancy thing. Calcium hydroxide mixes with carbon dioxide to form calcium carbonate, which is basically chalk. So calcium hydroxide is soluble in water. It will just make a clear solution. Chalk, as you know, doesn't dissolve well in water. If you take a stick of chalk and you mix it in water, you're going to have chalky looking water. So this is a nice little test, because if there is CO2 around, the calcium hydroxide will combine with it and turn to chalk, and you can't miss it. If you're bubbling lots of gas in there and there's no CO2, you'll also notice that there wasn't CO2, because if there was CO2, it would have turned chalky. So, we have this little system where, you can either suck through the short one, and it's kind of like having the room breathing. It's imagining it's kind of like having the room blowing down into the straw, right? If you're sucking here, you're creating a low pressure zone, the air rushes in. So if I suck through the shorter glass tube here, bubble the room air in here, I can see what happens to the water, or the lime water, which is the water with the calcium hydroxide. The other option here is I exhale through this longer tube, and my exhaled air is bubbling through, and I can see what happens to the lime water, to the calcium hydroxide. And again, if the air that's bubbling through there has lots of CO2, I'm going to see it because it's going to turn chalky. If there is not much CO2, I'll also notice because it's not going to turn chalky. So, what I'm going to do right now is just show you these, this video. It just lasts for 4 minutes of us doing this. And I'll discuss a little bit about some take-home messages. So like when you write up like what these observations are, you'll have a sense of like what is important to really take home from it. So this is just yes. So you don't have to write this down now if you don't have everything set, but you will eventually in your lab notebook kind of record what do you notice about the temperature, about the humidity, about the carbon dioxide based on what you see in this little 5-minute video.
Here we're going to do the exploring the respiratory system. This is part 1, composition of exhaled air. So we're going to compare the air that's here in the room, both temperature-wise and moisture-wise, and something else. And so we're going to start off looking at temperature. So right now the thermometer is showing room temperature. Next I am going to stick this.
Right, so you can see it's about 20 degrees, and this is all Celsius, right? So
in my mouth, but not touch any parts of my mouth, and I cleaned it. And I'm going to exhale or breathe out a few times, and we're going to see what happens to temperature. All right? All right, so if we zoom in there, you can see that the temperature has gone up. It looks like maybe 23, indicating that the air that I'm breathing out is, of course, warmer.
Right, so I mean, it's more like 20, it was probably 23 when she first looked at it and it started to drop again. Remember, degrees centigrade are bigger than degrees Fahrenheit, so that's actually, it's a sizable warming. So what does that tell us already, even? By knowing that the air that we're breathing out is warmer than the air that we breathed in. Just kind of on some thermodynamic level, what does that tell us about the thermodynamics of the human body?
The air inside our body is warmer than outside.
But I'm thinking more about kind of energy balance. Because so heat Heat is just energy, right? Remember we talked about heat being the energy of molecules jiggling and wiggling, right? When things are hotter, they got more energy to wiggle and jiggle. When they're colder, they're slower. So when we think of heat, it is kind of the most kind of random form of energy. It's kind of non-recoverable energy. It's hard to kind of, unless I guess you can use heat pumps and stuff, but basically, um, if you heated up the air, what did that mean about the your kind of energy balance in your body as that hot air is leaving? What's that?
Do we give off a lot of energy?
Yeah, we're losing energy. So what by taking in that air and heating it up and then just throwing it away, we're throwing energy away. You know, that's energy we're going to have to make up by like burning more fuel, you know, making more heat to keep our temperature homeostasis, right? So part of, remember, homeostasis is this balance, you know, trying to keep everything in the sweet spot. So anything that moves things away from whatever your balance point is going to be something you're going to have to deal with. So just by breathing, you are losing energy. Your temperature is kind of going down a little bit, and that's something that you're going to have to incessantly deal with if you don't want to just get colder, right? So like I said, this it's like not that big of a deal to notice, but then it actually is worth thinking about in terms of these homeostatic mechanisms and what your body actually has to pay attention to and deal with. And so the next part is going to be, again, it's going to seem pretty low tech and silly, but it's got some good take home messages.
Than the air that I was breathing in. So for the next part, we're going to take a look at what kind of water content we have in exhaled air. And so for this part, I'm going to use this piece of glass. And so you can see that right now there's no water vapor or condensation on this piece of glass as it's here in the room. So next I'm going to blow on it and we're going to see what happens.
Right. So first we had, you know, if it's just the room in the air doesn't create any condensation. So whatever water load is in the room air is not enough to condense out on there. Now we're going to see what her exhaled air does.
And so as you can tell, there is condensation occurring because my breath is both warmer and contains moisture, and so it hits the cold glass and we see the water vapor condense out.
Right. And again, you've all experienced this before in your life. But what is this telling us? Why do we act on a physiological, homeostatic kind of viewpoint? Why is this really important to pay attention to?
Are we losing water too?
Exactly. We are losing water. Every time you exhale, water is leaving your body, right? And that's water you've got to replace, or else you are going to dehydrate. This is going to be when we look at water balance a little later. We'll talk about insensible water loss. It's like no matter how much your body is trying to conserve water, or no matter how much ADH and how busy your kidneys are getting, you are going to lose about a liter a day to the environment. And a big part of that is just through your breathing. Every time you breathe out, you lose water to the environment. And that is water that has to be replaced, or else you are going to dehydrate. Right? Food, you can go for a month without eating food and you won't be happy, but you're not going to die. You can't go more than a few days without any water before you're dead, because you keep losing water, and without enough water, everything just, your blood turns to sludge and everything. So it's important to see this is a major place that no matter how much your body is trying to conserve water, you're losing it through breathing. Unless you're like in one of the Dune stories and you're breathing out through a little still suit or something and reclaiming your water and stuff. But for us, you have to just make sure you drink to replace that water. Okay, so that's the second part. And then the last part will be looking at carbon dioxide and through this kind of fun thing of bubbling through this calcium hydroxide, the lime water.
The third part of this experiment, we are going to investigate something else that's in my breath that I'm breathing out. And so for this, we're going to use lime water, which is in this bottle here. And so you can see it's semi-clear, it's pretty clear. And I'm going to pour about 150 ml. At least I need enough for this longer glass straw to be able to be fully immersed into the solution. And so then I put the stopper on, make sure I get a good seal, and check that this longer glass straw is down into the lime water. Then next, what we're going to do is I am going to put this straw, because this is where I'm going to put my mouth or lips on, and I am going to suck in air into my lungs, and that will force air to flow from the room into the longer straw. So we're going to get room air into the lime water, and then you know, we're making sure that I'm not breathing in any of the, or sucking in any of the fluid, because that straw is much shorter. All right, and so after that, we're going to switch the straw over here, and then the second part, I'm going to blow my breath into the lime water, and we're going to see what happens. All right, so let's start with getting room air into the lime water. So I'm sucking on this. And as you can see, there is nothing really happening. The lime water is still clear. So next, I am going to switch to the other straw here, and for this part, I'm going to blow my breath into the water, and let's see what happens. Here you can clearly see that the lime water has turned cloudy, and it's now up to you to read in your manual. There's a chemical reaction formula there, and then combine that with thinking about what is it in my breath that I'm breathing out that's part of that chemical formula that can cause this lime water to get cloudy, or in other words, obviously we're forming a precipitate, more cloudy particle that is making this a little bit cloudy.
So what do you think was in her exhaled air that caused it to become cloudy?
CO2.
Yeah, exactly, it's CO2. So again, that part one, again, it's relatively simple, but it's worth, I think it brings us some good take-home messages, thinking about losing heat and water with every exhale, which are important when you think about homeostasis. And also the idea that, your exhaled air has way more carbon dioxide, because that's a big part of your function, is to, your body is making it through cellular respiration, and then you got to get rid of it. The next part of the lab, I have to give you a little bit of background, and we're not going to do part 3 at all. So what we're going to do is I'm going to give you a little bit of background for part 2, and that's something you can actually do at home, and record your data. But I want to give you some background so you kind of have the context to think about it. And it's also the last little piece of the respiratory system that you need to know, like for your exam, which is basically, control of respiration. So unlike the heart, which is totally self-contained, right? If you yank somebody's heart out of their body, the pacemaker node is still going to keep the heart beating, and that's within the walls of the right atrium. For respiration, the neural circuitry that send out the messages that go breathe, 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 they're in the brainstem. So, basically, I'm not even going to go into the details. In the pons and the medulla are where you have these respiratory centers. We talked about the hypothalamus can modulate their activity, but the real kind of meat and potatoes of respiratory control are here in the pons and the medulla. One of the things that's non-intuitive, if you haven't seen this before, is what they are paying attention to decide how deeply and rapidly you need to breathe. And driven mainly by increasing CO2 levels. Okay, well, let me not write so sloppy. So the need to breathe driven so not oxygen. Even though you're thinking like, oh, if you're not having enough oxygen, I need to breathe more. The body doesn't care. You can even find these cool videos on there, or there's all sorts of horrible stories actually, where people die because they are not getting any oxygen, but they don't feel they need to breathe. If you breathed pure nitrogen, this like happened to some people in like the astronaut program. They walked into some room that was flooded with nitrogen. You walk in, and as long as you're ventilating, breathing in and out and in and out, CO2 does not accumulate. You're blowing off your CO2. So they never had this sense, I'm suffocating, because that would come from too high levels of CO2. They weren't getting enough oxygen. And so eventually they passed out and died, but they never knew what was happening until they passed out. I knew a guy in lab who kind of kind of just for fun, breathed like pure nitrogen until all of a sudden, just like clink, you could hear his head whack on the tank. Because it's hard to even know it's coming because you don't realize that you are running out of breath or you don't have enough oxygen. So this is kind of the most important take-home message is your body in general is not monitoring oxygen. You do have some oxygen sensors like in your carotid bodies and stuff, and I think in emphysema and stuff where you have chronically elevated CO2 levels in your body because you have trouble exhaling, you can get more hypoxic driven breathing. But for the most part, if you don't have enough oxygen, but you are blowing off all the CO2, you won't know anything's wrong until it's too late. So This is at the core of this lab. This is part 2 of the lab, is realizing that CO2, accumulating CO2 is ultimately what makes you feel like I gotta breathe. I'll give you hyperventilation, hypoventilation. Hyper, kind of excess. This would be like kind of deep, rapid breathing. Hypoventilation is shallow breathing. Again, if you think about the lungs as this kind of closed system where you're sucking in, breathing out, and there's always stale air mixing with fresh air. If you're doing just shallow breathing, hypoventilation, and you're even blowing out less than normal and then bringing new in, it's going to let carbon dioxide build up even more than normal in here, right? This is going to increase CO2 in the body, right? Because breathing out is what lets you expel CO2. So if you're breathing really shallowly, you're doing hypoventilation, CO2 is going to build up in your body. Conversely, for hyperventilation, if you're really doing, you are blowing out as much CO2 as you can. And then before it has a chance to build up, you're blowing it all out again. This is going to blow out lots of CO2. So the CO2 is going to be lower in the body. So that's important. CO2 is lower when you do this hyperventilation. So now we can do our little hypothesis. So I can use one other word, eupnea just means kind of normal, good breathing. So just kind of normal breathing. Right? U is like beautiful. So which case do you think you can hold your breath longer? After you've hyperventilated a bit or after you hypoventilated?
Hyperventilated.
Yeah, totally. If you've hyperventilated, you've blown off lots of CO2, it's going to take a lot longer for the CO2 levels to build up in your body to some level where you feel like, I gotta breathe. If you've been hypoventilating and you already have high levels of CO2 to start with when you start holding your breath, you're going to hit that critical level where you gotta breathe much sooner. That's a similar thing. Like in our lab, we're going to do rebreathing into a little bag. It's the same idea. If you're rebreathing, we saw exhaled air is high CO2 just from part 1. If you keep rebreathing the same air, that's also going to be increasing CO2 in your body. So when you're doing this lab, you're going to do this. In fact, maybe I should share, let me share the screen first. Wait, where did it go? Where did it go? All right. Oh, there it is. So, take 3 deep breaths and then you hold your breath as long as you can. This is going to be your baseline. And really just hold it as long as you can, and then you're gonna, at some point you can't. Then it says rest a while. Then it says breathe 20 times deeply and fairly rapidly. This is our hyperventilation. I should warn you that when you hyperventilate, see what's happening to your pH in your body if you're blowing off. There's very little CO2 in your body.
You become more alkaline.
You become more alkaline, and that actually constricts vessels to your brain, and you start to get dizzy and like kind of weird head rush. So don't do this where you're gonna, if you fall down, you're gonna hurt yourself. Because you could get a little, in fact, I promise you're gonna get that kind of whoa. That being said, don't have that whoa feeling be the feeling I need to breathe. Usually once you ride out that kind of weird dizzy head rush place, you can just keep holding your breath for a long time. So what you're gonna do is hyperventilate and then hold your breath for as long as you can. Again, you start a timer and you see how long that goes. And I should say, if you do this and you like barely hold your breath at all, you may try it again. That's something went wrong.
Can I ask a question?
Sure.
For question number 2, if that is shorter than after you hold your breath after 3 deep breaths, could that just be because like you're not relaxed?
No, I
Or
think
could it be longer?
usually it's because somebody got kind of scared by the dizziness and decided to breathe.
Okay, so it should be longer, like in a perfect world.
Not even in a perfect, yeah. I mean, I would say, assuming that you are actually just doing the procedure appropriately, hyperventilating, you can often like hold your breath twice as long. It's pretty dramatic how much longer you can hold your breath once you really blow off the CO2. Like if you go free diving, like snorkeling, you take a few deep breaths before you go down, and it really extends the amount of time you can spend swimming around underwater. You don't want to overdo it. If you overdo it, you can actually create a situation where you hold your breath so long, and especially as the pressure changes as you like swim back up to the surface, you can have not enough oxygen left before you feel the need to breathe, and you pass out underwater like a shallow water blackout, and you can drown. So you don't want to don't overdo the hyperventilation if you're gonna go snorkeling. But a minimal amount of hyperventilation is nice because it lets you spend a lot more time kind of cavorting with the fishes down there. So the next one, it says use appropriate precautions. Place a large plastic bag over the mouth and nose. Again, I always feel a little funny. It's like you always tell someone, this is how little kids die, right? So please don't kill yourself. Or if you're having your little kid do the experiment, don't kill your kid. Or don't convince your kid it's fun to play putting plastic bags over their head. That being said, plastic bags are nice because they're flexible, they're easy to seal. Let me. Like here's a bag from like bread. I'm gonna like kind of get rid of all the air in there. And what I really want to make sure is that I keep rebreathing the same air. So I'm gonna have it. Like 20 times. What happens a lot of times is people kind of cheat. They like suck in. It's like, wait, this is completely empty. There's nothing here. And I'm just leaking it around the edges, right? So a lot of times people will do this thing, breathe in and out of the, rebreathe in the plastic bag. And it's like, oh my God, I could have pulled my breath the longest of all. It's like, it's again, if you're holding your breath for a really long time after you've rebreathed into a plastic bag 20 times, something's wrong. That just doesn't happen. So make sure when you do this part, the rebreathing into the bag, you can use a paper bag, but they tend to not be big enough, plus they're harder to seal. Really make sure you're sealed around so you're really rebreathing your own exhaled air, which is going to, every time you exhale, it's going to be even more carbon dioxide, more higher concentrations of carbon dioxide. So by the time you're done with that, what do you expect when you try to hold your breath? Yes.
Not able to do it very long.
Not able to do it very long. The last part, I actually have to turn this thing off. You know, it says sprint around the building, but it can be wherever you're at. You could even sprint in place, you know, given that you're like maybe at home, but it's not like a like do look, I'm sprinting, right? This is really about getting, you know, like really by the time you're done, you should be like tired, right? You really, this should not be some loping gait or some like little jog in place. You really want to go into anaerobic respiration is the whole point of this. You want to go into oxygen debt, right? And once you're in oxygen debt, what do we know is going to be happening after you've used up these anaerobic pathways?
We gasp for air. We breathe.
Right? Why are we gasping for air though? Why do you, we talked about what do we call that condition after you've used up these anaerobic pathways and now you need to regenerate them? Remember, you've gone into glycolysis and you've made all this lactic acid, you've used up all this creatine phosphate, which has to get reconnected. Anybody remember the name for remember after you use these anaerobic pathways, it takes, I mean it came up in the blood pressure lab as well.
Oxygen debt.
Yeah, oxygen debt. You know, it's gonna take an extra like, you know, 11 liters of oxygen or something that is going to be busy working to recover from that anaerobic metabolism. So while you're sitting there, you've got all this stuff going on in your body, generating lots of carbon dioxide, even though you're just sitting there. Kind of like, you know, the same way we saw the blood pressure stayed high because there's lots of activity trying to send the blood and the oxygen around to recover after you did the Harvard step test. Right, so after you have done this exercise, you know, instead of like measuring your blood pressure after exercise, which is what you did last time, you're going to be measuring your ability to hold your breath after exercise, you know. And again, there's going to be kind of related because in both cases you're in oxygen debt, you're going to have increased metabolic activity, you're going to have increased blood flow to deal with recovering. It's also going to be a much faster generation of CO2 during that recovery process than a normal resting. So does that make sense? Right, so that's going to be this part. Part 2, I would like you to actually do. You just need a timer, measure a baseline breath hold, measure breath hold while you are doing hyperventilation. Do it when you're rebreathing your stale air, and then do it after, kind of sprint in place for 60 seconds would be fine if you're really just doing it high intensity. Be sure to interpret your results. Why does it make sense what you see in one case versus the other? And there's this, exploring the respiratory COVID edition data. So it says, do at home, record your data in your lab manual and kind of interpret it. And here's use this data, use your data along with the group data, right? We always use group data to make sure that your data is consistent with what we find. So here you'll be able to see what the data was for a number of subjects, on average, and you can put your data into context there. And again, don't do part 3. So, what time is it? Are there any questions about any of that?